Hello there, and welcome to the Sleepless Scientist. Tonight, we embark on a gentle exploration of two things that shape absolutely everything: time and space. They surround us in every moment, invisible and yet fundamental to existence itself. We move through them every day without truly knowing them. But what if we paused to wonder? What if we asked the simple questions that physicists have pondered for centuries? Tonight, we'll trace the story of how humans came to understand these mysteries, from the brilliant insights of Einstein to the mind-bending truths revealed by modern science. We'll explore how time and space are woven together, how gravity bends the very fabric of reality, and what might lie at the edges of everything we can see. This is a journey through the cosmos, but it's also a journey through ideas. So settle in, let your mind wander through the stars with us. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The story of time and space. There was a moment, an impossible, unknowable moment, when neither time nor space existed. Before the universe began, before anything could be measured or marked or remembered, there was only potential. Then came the beginning, and with it came everything. The story of time and space is the story of reality itself. For thousands of years, humans looked up at the stars and wondered. They watched the sun move across the sky and measured the passing seasons. They built clocks. They created calendars. They tried to pin down the nature of existence. But for most of human history, we had it backwards. We thought time was absolute, a river flowing at the same speed for everyone, everywhere. We thought space was an empty container, just sitting there, waiting for things to fill it. Both of these ideas felt true. They matched our everyday experience, but they were incomplete. Then, at the beginning of the 20th century, one man changed everything. His name was Albert Einstein, and his ideas would shatter our most basic assumptions about reality itself. This is the story we'll tell tonight, how we learned that time and space are not what they seem, and how two things we take for granted are actually the most profound mysteries in the cosmos. What is time? Think about this for a moment. What is time, really? We measure it, we live it, we fear running out of it. But if you try to define it simply, it slips away like water through your fingers. Time is not a thing you can touch. You cannot see it or hold it, yet it touches everything. It is the sense of before and after, the feeling of duration, the way one moment becomes another. We experience time as a flow, a current carrying us from the past, through the present, into the future. But is that what time actually is? Or is that just how our minds interpret something far stranger? In physics, time is treated as a dimension, much like width or height. You can move forward and backward through space relatively easily, but time feels different. You can only move forward through time into what hasn't happened yet. Is this a law of physics, or is it something about consciousness? Scientists still debate this. What we know is that time allows change. Without time, nothing could happen. Without time, there would be no birth or death, no growth or decay, no memory or anticipation. Time gives the universe a narrative. It gives existence direction. And yet, as we'll discover tonight, time is far more flexible than we ever imagined. What is space? Space is loneliness and vastness. It is the distance between you and the stars, and the distance between atoms in your hand. It is where things exist. Yet space, like time, is difficult to define. We think of space as an empty void, a blank stage on which the drama of the universe unfolds. We imagine it as this invisible grid, infinite in all directions, waiting for matter and energy to fill it. But what is space when nothing is in it? Does it still exist? These are not simple questions. Space has three dimensions that we experience directly: height, width, and depth. We can move freely in each direction. Distances make sense to us. A mile is a mile. A kilometer is a kilometer. Or is it? Einstein showed us something profound. Space is not fixed. It is not unchanging. The distance between 2 points depends on how you're moving and how strong the gravity is around you. Space can stretch. It can compress. It can be warped by massive objects. Space is dynamic. It's alive in a way. It responds to matter and energy. And astonishingly, space has a beginning. It wasn't always there. Space itself came into existence at a specific moment. That moment was the Big Bang, the birth of time itself. Imagine standing at the absolute beginning of everything, not at the beginning of Earth, or even the beginning of our galaxy, the beginning of time itself. This is almost impossible to imagine, because we use time to make sense of the world. We ask what came before, but there was no before. Before the Big Bang, there was no time, no past, no sequence of events leading up to it. This is not poetic exaggeration. It's what the mathematics of physics tells us. Time emerged with the universe. It was born in the first impossibly small fraction of a second after the Big Bang. The universe was so hot, so dense, so different from anything we know today, that the very laws of physics as we understand them break down. Scientists call this moment the singularity. It was a point of infinite density, infinite temperature, infinite mystery. What happened at the singularity? We don't know. Perhaps time itself didn't exist in the way we understand it. Perhaps past, present, and future were all tangled together in some form we cannot grasp. What we do know is that time had a beginning. It did not always exist, and it is connected to the fate of the universe itself. When the universe dies, if it dies, time may die with it. The beginning of space at the Big Bang. Space, too, came into being with that first moment. There was no space before the Big Bang, because there was nowhere for space to be. Space is the stage, and the stage was created at the moment of creation. At the Big Bang, all of space, every cubic inch of the entire universe, erupted into existence at once. But it didn't expand into space that was already there. Rather, space itself began to expand. This is a crucial distinction. The universe isn't like a balloon expanding into the air around it. The balloon's surface is expanding, and there's empty space outside the balloon. But with the universe, there is no outside. Space itself is growing. New space is being created constantly, and everything in the universe is being carried apart by this expansion. In the first moments after the Big Bang, space was impossibly tiny and impossibly hot. Then it expanded. It cooled. The first particles formed. Atoms were born. And after hundreds of millions of years, stars ignited and galaxies formed within this expanding space. But here's the beautiful part. We can still observe the aftermath of that first moment. We can see ancient light that has been traveling through space for over 13 billion years. This light carries information about the earliest moments of creation. It tells us stories about the birth of space itself, a universe expanding into the unknown. The universe is not static. It is not sitting still, waiting for time to pass. It is expanding, and this expansion is accelerating. Galaxies are moving away from each other, and the farther apart they are, the faster they're moving apart. This was one of the great discoveries of the 20th century. It overturned the assumption that had held sway for centuries, that the universe was eternal, unchanging, and infinite in extent. Now we know it had a beginning. But does it have an end? The universe is expanding into nothing. There's no edge, no boundary, no wall where space stops, yet it's still expanding. The space between galaxies is literally stretching. New space is being created all the time. Billions of years from now, the galaxies in the far distance will be so far away that their light will never reach us. Future generations will look up at a sky with far fewer stars. They won't know what we know about the universe's vastness, because most of it will be hidden behind the veil of expansion. We are living in a golden age of cosmic visibility. We can see farther than any humans will ever see again. We witness galaxies billions of light years away. We observe the universe as it was when it was young, and we know that this gift is temporary, the fabric of space-time. Here's something surprising. Time and space are not separate things. They are two aspects of the same thing. Physicists call it space-time. Imagine space and time woven together, like threads in a vast fabric. You cannot move through space without moving through time. You cannot move through time without existing in space. This insight came from Einstein, and it changed everything. Before Einstein, physicists treated space and time as independent dimensions. Time was absolute, space was absolute, but Einstein showed that they're intertwined. They bend together, they curve together, they age together. When you move through space, time passes more slowly for you than for someone standing still. When you experience strong gravity, time moves differently for you. These aren't just theoretical ideas. We've measured them. Satellites in orbit experience time at a slightly different rate than people on Earth. This effect is so real that if we didn't account for it, our GPS systems would fail. The very idea of space-time suggests that the past, present, and future might all exist simultaneously in some sense. The fabric of space-time contains all moments at once. Whether this is truly the case, or merely a useful way of describing reality, remains one of the deepest questions in physics. How space and time are connected. The connection between space and time is not just poetic metaphor, it's mathematical. It's real. When you move faster through space, time passes more slowly for you. When you move slower through space, time passes more quickly. There's a trade-off. The speed of light plays a central role in this connection. Light always travels at the same speed, no matter who measures it or how fast they're moving. This constancy of light's speed creates a mathematical relationship between space and time. The faster you go through space, the more your clock slows down relative to a stationary observer. This is time dilation, and it's one of the most counterintuitive discoveries in physics. An astronaut traveling at near light speed ages more slowly than people on Earth. This isn't science fiction. It's as real as gravity, and it reveals something profound. There is no universal now. Different observers moving at different speeds through space experience different nows. Events that are simultaneous for one observer are not simultaneous for another. This seems to violate common sense, but when you examine it carefully, it makes sense. Space and time are woven together so tightly that they cannot be separated. They are two faces of a single reality, the curvature of the cosmos. Look up at the night sky. It seems flat. The stars seem to be painted on a distant flat dome above us. This is how the cosmos appeared to ancient astronomers. But space is not flat. It is curved. Einstein's great insight was that gravity is not a force in the traditional sense. It is not a thing that pulls. Rather, gravity is curvature. Massive objects curve the space around them, and other objects follow the curves. Imagine space as a piece of rubber, stretched tight. Now place a bowling ball on it. The ball creates a dip, a curve in the fabric. A marble rolling nearby will curve toward the bowling ball, not because of any force pulling it, but because the surface itself is curved. This is gravity. The sun curves space around it. Planets follow those curves. We think we're being pulled toward the sun, but really, we're following the curves of space-time that the sun creates. The curvature of space is not uniform throughout the cosmos. Where there's mass and energy, space is more curved. In empty voids between galaxies, space is relatively flat. And in the hearts of black holes, space is curved so dramatically that even light cannot escape. The curvature of the cosmos tells us about the shape of the universe itself. Is it flat? Is it spherical? Is it saddle-shaped? These are not idle questions. The shape of space determines the fate of the universe. Einstein's great discovery. In 1905, a young physicist named Albert Einstein sat in a patent office in Switzerland, and changed our understanding of reality. He didn't have access to the world's best laboratories. He didn't have a team of researchers, but he had imagination, and he had mathematics. Einstein imagined himself riding on a beam of light. He wondered what the universe would look like from that perspective. This thought experiment led him to a radical conclusion. The laws of physics must be the same for all observers, moving at constant velocity. Light always travels at the same speed. Space and time must be relative. 10 years later, Einstein developed his theory further. He discovered that gravity was not a force, but the curvature of space-time itself. These ideas were not immediately accepted. Many physicists found them incomprehensible. Some dismissed them as philosophical speculation rather than science. But gradually, experiments proved Einstein right. The sun bent starlight during a solar eclipse, exactly as Einstein predicted. Atomic clocks showed that time really does move at different rates, depending on velocity and gravity. Einstein's vision proved correct again and again. And his ideas didn't just explain the world. They opened entirely new questions. They made us wonder what else we might be wrong about. The theory that changed everything. Einstein's theory of relativity came in two parts: special relativity and general relativity. Special relativity, published in 1905, dealt with objects moving at constant velocity. It introduced the famous equation E equal mv, showing that mass and energy are interchangeable. It revealed that time and space are relative, not absolute. Then came general relativity in 1915, which dealt with gravity and acceleration. This was the revolution. General relativity showed that gravity is not a separate force acting on objects. Instead, massive objects bend the very fabric of space and time around them. This single idea explains so many mysteries. It explained why Mercury's orbit is slightly different from what Newton's laws predicted. It predicted the existence of black holes. It showed that time moves at different rates, depending on gravity. It suggested that the universe might have a beginning. General relativity is the most elegant theory in physics. From just a few principles, it generates explanations for almost everything we observe in the cosmos, and yet it remains incompatible with quantum mechanics, the theory that governs the subatomic world. Physicists still search for a unified theory that reconciles these two great pillars of modern science. The nature of relativity. Relativity sounds confusing, but the basic idea is simple. There is no absolute reference frame. There is no special vantage point from which we can say this is truly how things are. Everything is relative to the observer. Two people moving at different speeds through space will measure distances and durations differently. Neither is wrong. Both are right from their own perspective. This seems to suggest chaos. If everything is relative, how do we know anything? The answer is that some things are absolute. The speed of light is absolute. Physical laws are absolute. The space-time interval, a combination of space and time, is absolute. These constants provide structure to the universe. They make it comprehensible. Relativity doesn't mean everything is subjective, or that reality depends on opinion. Rather, it means that how we measure space and time depends on our state of motion. But what we're actually measuring, the underlying reality, remains consistent. A clock in motion ticks more slowly than a stationary clock. This is not an illusion, it's a real effect. Yet both observers can agree on what happens. The mathematics works. Everything is consistent. This is the beauty of relativity. It seems strange and counterintuitive, yet it's more logically consistent than anything we had before. Time moves differently everywhere. Close your eyes and imagine this. Two twins. One stays on Earth. The other travels to space at nearly the speed of light, orbits a distant star, and returns. When they meet again, the twin who traveled has aged much less than the twin who stayed behind. They might have been the same age when separated, but now one is much younger than the other. This is not fantasy. This is what Einstein's equations predict, and it's been verified experimentally with atomic clocks. Time literally moves at different rates, depending on your circumstances. In the depths of a strong gravitational field, time moves more slowly. On a mountaintop, where gravity is slightly weaker, time moves more quickly. This effect is tiny for everyday objects, but it's real. Astronauts in orbit age slightly less than people on Earth. The difference is imperceptible to humans, but it's measurable with precision instruments. Near the event horizon of a black hole, the effect becomes extreme. Time nearly stops. An observer falling into a black hole would see the entire future of the universe flash before their eyes, while they themselves seem to fall forever. Time is not a universal constant. It flows at different rates throughout the cosmos. It's slower where gravity is strong. It's faster where gravity is weak. This is one of the most profound implications of relativity. The speed of light and the flow of time. The speed of light is the speed limit of the universe. Nothing can go faster. This speed is always the same, about 186,000 miles per second. And this constancy of light speed is intimately connected to how time flows. When something moves faster through space, it moves more slowly through time. The trade-off is perfect. The total speed through space-time is always the same. An object at rest moves through time at maximum speed. As it accelerates through space, its progress through time slows down. At the speed of light, time stops entirely. This is why light doesn't experience time. A photon emitted from the sun feels no duration in reaching Earth, no matter how far away we are. From the photon's perspective, it travels from the sun to Earth instantaneously. For us, it takes 8 minutes. Both perspectives are correct. This relationship between speed through space and speed through time explains so much. It explains why you can't accelerate matter to the speed of light. It would require infinite energy. It's because as you approach light speed, more and more energy goes into slowing your clock rather than accelerating you further. The universe enforces this speed limit with absolute precision. No massive particle has ever been observed exceeding light speed, and the mathematics suggests none ever will. Light itself seems to be the exception. How motion changes time itself. Motion doesn't just affect time. Motion is fundamentally connected to time. The faster you move through space, the more slowly time passes for you. This isn't metaphor. It's measurable. Satellites in orbit move at high speeds. Their atomic clocks tick slightly slower than identical clocks on Earth. We can measure this with instruments. But here's what makes it profound. There's no absolute standard of motion. Motion is relative. You're always moving relative to something else. Yet time dilation is not relative. It's absolute. If an astronaut leaves Earth at high speed and returns, they will have aged less than people on Earth. This is not a matter of perspective. It's an observable fact. The twin who traveled really is younger. This suggests something deep about reality. Time is not smooth and universal. It's interwoven with motion and position in space. Your clock is slowing down right now, traveling through space on this planet. If you could see a clock in a satellite, you'd see it ticking slightly slower than your clock. These differences accumulate. Given enough time and enough speed, the effects become dramatic. An astronaut could travel for what feels like 5 years, while 30 years pass on Earth. They would return to a world that had aged differently than they had. The mystery of time dilation. Time dilation is real, yet it remains mysterious. Why does motion change the rate at which time passes? Why does gravity do the same thing? The answer, Einstein showed us, is that they're two aspects of the same phenomenon. Motion and gravity create equivalent effects on space-time. This is the principle of equivalence. From the inside, you cannot tell the difference between acceleration and gravity. An astronaut in a rocket accelerating at 1 g feels the same as standing on Earth's surface. And just as standing on Earth changes your experience of time relative to someone high in space, acceleration does too. The mystery goes deeper. We still don't fully understand why space-time has this structure. Why should time be connected to motion and gravity in this particular way? The mathematics tells us it is, but the question of why remains open. Some physicists wonder if there are deeper principles at work, principles we haven't yet discovered. Others suggest that the structure of space-time is fundamental to reality itself, with no further explanation possible. Time dilation is not just an exotic effect that happens at high speeds. It's constantly happening everywhere. It's just too small to notice in everyday life, but it's always there, woven into the fabric of reality. Space bends under gravity. Gravity is not a force pulling downward. It's the bending of space itself. This is almost impossible to visualize, yet it's what the equations show. Imagine a flat piece of paper. Place a heavy ball in the center. The paper bends and curves around the ball. Now imagine that the paper represents space, and the curve represents the presence of a massive object. Smaller objects placed on the paper roll toward the ball, not because they're being pulled, but because the surface is curved. This is gravity. A star bends the space around it. Planets follow the curves of this bent space. They orbit because they're following geodesics, the straightest possible paths through curved space-time. When we experience gravity, we're actually following a geodesic. The ground beneath us is stopping us from following the curve of space-time around the Earth. Without the ground, we would fall straight down that curve. The more massive an object is, the more severely it bends space. A black hole bends space so extremely that nothing can escape, not even light. The curvature becomes so sharp and so deep that everything within a certain distance must fall inward. Space itself becomes a trap. This picture of gravity as space-time curvature unifies three distinct ideas into one elegant principle. Gravity, space, and time are not separate things. They're aspects of a single reality, the universe as a living fabric. Space-time is not inert. It's not just a passive container for matter and energy. It's dynamic. It responds. It lives. When you move through space, you curve it. When you accelerate, you warp it. This is expressed mathematically in Einstein's field equations, which relate the curvature of space-time to the presence of matter and energy. But there's something almost poetic about this idea. The universe is not a machine with time as a ticking clock and space as an empty void. Rather, they're woven together into a fabric, and this fabric is responsive. It feels the presence of massive objects. It curves around them. It allows for motion and change. The universe is alive in this sense, not alive as we normally think of life, but alive as a system that responds and evolves. Ripples can propagate through space-time. These are gravitational waves. Accelerating masses create waves that ripple outward through space and time. These waves were predicted by Einstein and observed experimentally only recently, in 2015. When we detected them, we confirmed that space-time is indeed a real thing. It can vibrate. It can oscillate. It's not just mathematics. It's physical. When two black holes collide billions of light years away, they send ripples through the fabric of reality. Those ripples travel across the universe, bending space and time as they pass. And we can feel them. We can measure them. How planets and stars curve space. Every massive object curves the space around it. The Earth curves space. The Sun curves space more dramatically because it's more massive. A white dwarf curves space even more intensely because its mass is compressed into a smaller volume. A neutron star is more extreme still, and a black hole represents the ultimate curvature. Space so bent that it creates a one-way trap. The curvature of space explains planetary orbits perfectly. Mercury, being closest to the Sun, experiences the most curvature. Its orbit should, according to Newton's laws, precess at a certain rate. but observations showed Mercury's orbit precessed slightly faster than Newton predicted. When Einstein calculated what general relativity predicted, the numbers matched perfectly. This was one of the first confirmations that Einstein was right. Every star and planet creates a dimple in the fabric of space. Smaller bodies orbiting around them follow these dimples, the curves of bent space-time. This is why planets don't escape into space, and stars don't randomly fly apart. They're held in place, not by invisible pulling forces, but by the geometry of the space around them. We can map these curves, we can calculate them, and remarkably, the curvature gets stronger the closer you approach the massive object. Near the event horizon of a black hole, the curvature becomes infinite. Space is twisted into a point. This suggests that our current understanding breaks down at the extreme. But within the normal cosmos, the picture is clear. Gravity is geometry. The nature of gravity. Gravity is the most familiar force in our lives, yet it's the weakest of the four fundamental forces. It's the force that keeps us on the ground, that makes objects fall, that holds planets in orbit and stars in galaxies. Yet gravity is also unique. Unlike the other forces, gravity cannot be shielded. You cannot hide from gravity. Any object with mass creates a gravitational field. The larger the mass, the stronger the field. But here's the strange thing. Gravity is the only force that's always attractive. Electromagnets can repel each other. Nuclear forces can push apart, but gravity only pulls. It never pushes, and gravity acts instantly across any distance. If the sun suddenly disappeared, the Earth would immediately begin moving in a straight line, rather than continuing to orbit, at least. This is what Newton's laws suggest. But relativity says nothing can travel faster than light, including the effects of gravity. So how can gravity act instantly? The answer is that gravity doesn't propagate through space. Rather, gravity is the structure of space itself. The curvature is always there. It doesn't need to propagate. This subtle distinction resolves the paradox. Gravity is not a force that travels. It's a property of space-time, and that property is always present. Why falling is just following curved space. Here's a mind-bending idea. When you fall, you're not moving through space the same way you normally do. When you jump off a building, you follow a geodesic, the straightest possible path through curved space-time. The Earth's mass has bent the space around it into a curve. You're simply following that curve. This is what falling really is. It's not being pulled down by an invisible force. It's following the natural path through curved space. An airplane in flight is constantly falling toward Earth. It's not sustained by air pressure. Rather, the pilot continuously applies force to prevent it from following the geodesic. The straight path through space-time near Earth curves downward, so the plane, to maintain altitude, must accelerate upward. It's continuously following a curved path instead of the geodesic. This is why astronauts in orbit feel weightless. They're actually falling toward Earth. They're following the geodesic around the planet. The spacecraft is falling with them. They feel no support, so they feel no force. Yet they're accelerating downward at 9.8 meters per second squared, just like you'd expect from gravity. The illusion of weight comes from standing on the ground, which prevents you from following the geodesic. The ground accelerates you upward, so you feel pushed down. Once you understand this, everything makes sense. Gravity is not pushing. It's not pulling. It's geometry. The warping of light by massive objects. Light travels in straight lines, as far as we know, but in curved space-time, a straight line is not what we expect. Light follows the curvature of space itself. This is why light bends around massive objects. In 1919, astronomers observed that starlight bent around the sun during a solar eclipse. The star's light, traveling through space, curved by the sun's mass, was deflected. The deflection was exactly what Einstein predicted. This observation made Einstein famous. It proved that space really is curved by mass. Light always takes the path of shortest distance through space. But when space is curved, the shortest path is not a straight line, as we normally imagine it. The shortest path is a geodesic, and geodesics curve. The more massive an object, the more it bends the path of light. A massive galaxy can act as a lens, bending and magnifying the light from even more distant galaxies behind it. Gravitational lensing has become a tool for astronomers. By observing how light bends around massive clusters of galaxies, we can map the distribution of dark matter we can't see directly. The warping of light reveals the shape of space itself, and it confirms, over and over, that Einstein was right. Mass bends space, and light follows those bends. The proof of Einstein's vision. The history of relativity is a history of confirmation. Again and again, predictions from Einstein's theories have been verified by observation. The bending of starlight during a solar eclipse, the precession of Mercury's orbit, the gravitational redshift, light losing energy as it escapes a gravitational field, time dilation, measured by atomic clocks on airplanes and satellites, GPS systems that must account for relativity, or they fail. And most recently, in 2015, gravitational waves. When two black holes spiral into each other, billions of light years away, they create ripples in space-time. These ripples traveled to Earth. We detected them with instruments of exquisite sensitivity. The detection confirmed that space-time is real. It can vibrate. It can oscillate. We've observed the aftermath of black hole collisions. We've seen neutron stars merging. Each event generates gravitational waves that confirm relativity's predictions with stunning precision. No prediction of Einstein's theory has ever been falsified. Where we've been able to test it, it's always correct. This is remarkable. Most scientific theories eventually encounter edge cases where they break down, but relativity remains robust. Some physicists believe that, like Newton's laws, it might someday be superseded by something more fundamental. But for now, relativity remains the best description of space, time, and gravity we possess. The expanding universe. The universe is not static. It's growing. Galaxies are moving away from each other, and the farther apart they are, the faster they move. This was discovered in the 1920s and 1930s by astronomers using telescopes and spectroscopy. They observed that light from distant galaxies was shifted toward the red end of the spectrum. This red shift indicated that the galaxies were moving away from us. The more distant the galaxy, the larger the red shift. The universe was expanding. This discovery was shocking. Most scientists had assumed the universe was static and eternal, but the observations were clear. Space itself was stretching. Galaxies weren't moving through space like objects through water. Rather, the space between them was increasing. The universe was getting less dense. The galaxies were not being pushed apart by some explosion at the beginning. Rather, the fabric of space was expanding everywhere at once. This expansion is ongoing. Looking back in time using telescopes, astronomers see that the universe was more compressed in the past. Tracing this backward mathematically, you arrive at a beginning point, a singularity, the Big Bang. The expansion rate isn't uniform. It's accelerating. Something called dark energy is pushing the universe apart faster and faster. We don't know what dark energy is. It remains one of the greatest mysteries in physics, but its effects are undeniable. Space that stretches itself. Imagine a piece of rubber, stretched tight. Mark several points on it with dots. Now pull the rubber at both ends. The rubber stretches. The distance between the dots increases. But notice, the dots themselves don't move through the rubber. The rubber itself expands. This is how cosmic expansion works. Galaxies aren't moving through space like ships through an ocean. Rather, space itself is expanding. New space is being created. The galaxies are carried apart by this expansion. It's crucial to understand that this expansion has no center. There's no point from which galaxies are being flung outward. If you were in a distant galaxy, you'd see all other galaxies moving away from you. The expansion is uniform throughout space. Every point in space is equivalent. In this sense, the universe is homogeneous, the same on average everywhere. But also, the universe is expanding faster in empty regions between galaxies than in regions where gravity holds galaxies together. Gravity is strong enough to resist the cosmic expansion on small scales. Galaxies held together by gravity don't expand. Clusters of galaxies held together by mutual gravity don't expand. But on the largest scales, between galaxy clusters, the expansion dominates. Space stretches. It carries galaxy clusters apart, and the space between them continues stretching, creating ever greater distances. Galaxies moving apart forever. The trajectory of galaxies seems clear. They're moving apart now. The evidence is overwhelming, but will this continue forever? Will galaxies eventually be so far apart that they can never interact again? Or will something cause the expansion to reverse? The answer depends on the mysterious dark energy. If dark energy is truly constant, if it really is just the property of space itself, then expansion will continue accelerating forever. Galaxies will move apart ever faster. The far future of the universe, in this scenario, is eternal expansion. All the stars will eventually burn out. The universe will become cold and empty and dark. But we're not certain dark energy is constant. It could change, it could weaken, or it could strengthen. The search for dark energy is one of the great endeavors of modern cosmology. We've built instruments to measure its properties. We've watched distant supernovae, using them as cosmic measuring sticks to track the expansion rate. The universe seems to have transitioned from decelerating expansion to accelerating expansion a few billion years ago. At that moment, dark energy overtook gravity as the dominant force governing cosmic evolution. What this means for the ultimate fate of the universe depends on what happens next. For now, all signs point to continuing expansion. Galaxies will drift apart forever, ever farther, ever faster. The illusion of an edge. We speak of the edge of the observable universe. We say there's a distance beyond which we can't see. But there's no actual edge, no wall, no boundary, where space ends and something else begins. The edge we see is an illusion created by the finite speed of light and the finite age of the universe. Light has been traveling since the Big Bang, about 13.8 billion years ago. In that time, light from the most distant regions has just barely reached us. We call this the cosmic horizon. Beyond it, we don't see, not because space ends, but because the light hasn't had time to reach us. If we were to wait another billion years, light from even more distant regions would arrive. We'd see farther. There's no actual edge to space. The universe is not a sphere with a boundary. Rather, it's infinite, or if it's finite, it has no edge in the way a sphere or cube does. It could have a different topology, like the surface of a donut, with no edge anywhere. The absence of an edge is difficult to visualize. We're used to things having boundaries, but space might not. The universe might be infinite. In that case, it truly has no end. It extends forever, in all directions. Somewhere out there, beyond the cosmic horizon, galaxies exist that we will never see, and beyond those, more, forever. What lies beyond what we can see? Our telescopes can see back in time to when the universe was young, but there are limits to what we can observe. The cosmic microwave background, the afterglow of the Big Bang, surrounds us in all directions. It marks the edge of the observable universe, not because space ends there, but because that's how far light has traveled in the time since the Big Bang. Beyond that light, if you could somehow see, there would be more universe, but we cannot see it. Light from those regions hasn't reached us yet. This doesn't mean nothing is there. The universe beyond our cosmic horizon is surely filled with galaxies, stars, and planets. Some physicists speculate about parallel regions with their own big bangs, their own universes, the multiverse, they call it. If the universe is truly infinite, then somewhere out there, conditions are being repeated. Somewhere another Earth exists. Somewhere another you reads another version of this script. These ideas remain speculative. We have no direct evidence for multiple universes, but they follow logically from our understanding of an infinite cosmos. The vastness is difficult to comprehend. We try to wrap our minds around it, but our brains evolved to understand the size of continents and oceans, not the cosmos. The scales are simply too large, yet beyond what we can see, more exists, unfathomably more. The universe is stranger than we imagine. The observable universe. The observable universe is the sphere of space from which light has had time to reach us. It has a radius of about 46.5 billion light years. This is not the actual size of the universe. This is just the part we can potentially observe. Beyond this boundary, light hasn't reached us because the universe hasn't existed long enough, or because the expansion has carried that light away faster than it can approach. Within the observable universe, we've mapped about 2 trillion galaxies, 2 trillion, each containing hundreds of billions of stars, each star potentially harboring planetary systems. The numbers become meaningless. They're too large for the human mind. We can say them, 2 trillion, but we can't truly grasp them. If you tried to count to 1 trillion, one number per second, it would take 30,000 years. And that's just counting, not comprehending the scale. Within the observable universe, there's structure. Galaxies are not randomly distributed. They clump together into groups and clusters. These clusters are arranged into filaments. The universe looks like a vast web, with galaxies strung along threads of gravity and vast empty voids between them. The observable universe is what we can know. Everything beyond it is forever hidden from us by the cosmic horizon. In this sense, the observable universe is our universe. It's all we can ever study or understand directly. Light is a messenger of the past. When you look at the stars, you're looking into the past. The light from the nearest star, Proxima Centauri, takes 4.2 years to reach us. When you see Proxima Centauri, you're seeing it as it was 4.2 years ago. More distant stars carry even older light. The Andromeda Galaxy is so far away that its light has been traveling for 2.5 million years. When you look at Andromeda, you see it as it was 2.5 million years ago. Our ancestors were not yet fully human when that light began its journey. And the most distant galaxies we observe are so far away that their light has been traveling for over 13 billion years. We're seeing them as they were when the universe was young, in a very real sense. Telescopes are time machines. By looking at distant objects, we look backward through cosmic history. We see how the universe was in earlier eras. We watch galaxies being born. We observe the universe's youth. This is why astronomers are so excited about the James Webb Space Telescope. It can see even farther back, to even more ancient times. The light from the earliest galaxies carries messages about the universe's infancy. These messages are written in patterns of light and energy. Decoding them tells us about the beginning of everything. Light is the universe's way of sending messages across time and space. Without light carrying information, we'd know nothing about anything beyond the reach of our hands. How looking far means looking back. The deeper we look into space, the farther back in time we see. This is not accident. It's a direct consequence of light traveling at a finite speed. Imagine time layered, like the rings of a tree. Each ring is a moment in the past. As you look outward in space, you penetrate deeper into these rings. The most distant objects are the oldest. When telescopes look at the edge of the observable universe, they see almost back to the very beginning. They see galaxies as they were just a few 100 million years after the Big Bang. From these ancient images, we reconstruct the history of the universe. We see how galaxies formed, how they merged and evolved, how the cosmic web developed. We watch the universe age before our eyes. In a poetic sense, looking at the distant universe is like reading the biography of existence. The early pages tell of a hot, dense, young cosmos. The middle pages show the emergence of structure. The most recent pages show galaxies like our own, mature and settled. We're reading the cosmic story, and we're at the part where conscious beings have emerged to understand it. The most distant objects we see are the most ancient, but they're so far away that their light is extremely faint. Detecting them requires the most sensitive instruments ever built. Yet we persist in the attempt because these ancient objects contain crucial information. They show us how the universe began. They reveal the truth about our origins. The speed limit of reality. Nothing travels faster than light. This isn't just a rule. It's a fundamental property of space-time. The speed of light, about 186,000 miles per second, is built into the fabric of reality. It emerges naturally from Einstein's equations. It cannot be violated. This speed limit seems arbitrary. Why is it exactly that speed and not some other speed? Physicists still wonder, but the constancy of the speed of light is crucial. It's what allows for causality. It prevents paradoxes. If something traveled faster than light, it could arrive at a destination before it left its starting point. From the perspective of certain observers, this would violate the arrow of time. It would make cause and effect meaningless. The universe would be chaos. The speed of light preserves the structure of reality. It ensures that causes precede effects. It guarantees that information flows in a sensible direction through time. Nothing with mass can reach the speed of light because it would require infinite energy. As you accelerate an object, you're not just giving it more speed, you're increasing its momentum and energy. The faster it goes, the more energy is required to accelerate it further. At light speed, acceleration would require infinite energy. So massive objects can approach light speed, but never reach it. Only massless particles like photons travel at light speed. They have no rest mass. For them, light speed is the only possible speed. Why nothing can go faster than light? The reason nothing can exceed light speed is embedded in the mathematics of relativity. As an object approaches light speed, its momentum increases without bound. Its energy increases without bound. To accelerate it further requires more energy than exists in the universe. But there's a deeper reason. Speed through space and speed through time are related. Moving faster through space means moving slower through time. At light speed, time stops. You cannot go faster than light because you cannot travel faster through time than at zero rate. You've hit the limit. There's nowhere faster to go. The universe has built-in symmetry. The total speed through space-time is constant. You can move fast through space and slow through time, or slow through space and fast through time, or anywhere in between, but you cannot exceed the total. The speed of light is this universal constant. It's the speed limit because it's the speed at which all observers agree, regardless of their motion. Different observers will disagree about distances and durations, but everyone agrees that light travels at light speed. This universal agreement is what makes relativity coherent. It's what allows physics to work. If light speed varied, if it were relative like other speeds, everything would fall apart. The universe needs a universal speed limit to maintain consistency. The meaning of a light year. A light year is the distance that light travels in 1 year in a vacuum. It's about 5.88 trillion miles. It's not a measure of time, though the name suggests it. It's a measure of distance, but defined in terms of light and time. The nearest star to Earth is about 4.2 light years away. This means that light from that star takes 4.2 years to reach us. The Andromeda Galaxy is 2.5 million light years distant. The farthest galaxies we can see are over 13 billion light years away. These numbers have a poetic quality. They tell us about distance in terms of time. The farthest objects we see are so far that their light has been traveling for longer than the recorded history of human civilization. Light years show the scale of the cosmos in a way that miles or kilometers cannot. They make the vastness tangible. They make us realize that space is so large that even light, the fastest thing in the universe, takes billions of years to cross it. If you traveled to the nearest star at the speed of the fastest spacecraft humanity has ever built, it would take 50,000 years. For the Andromeda Galaxy, it would take over 2 billion years. These are not just numbers, they're testaments to the immensity of space. Light years remind us that we're not just small in size, we're small in the distances we can traverse. The universe is vast beyond comprehension. The distance between stars and galaxies. Stars are not evenly distributed through space. They cluster together into galaxies. Galaxies cluster into groups and filaments, and between these structures, there are vast empty voids. The nearest star to Earth is Proxima Centauri, 4.2 light-years away. That's about 250,000 times farther than the distance from Earth to the Sun. The distance is staggering, yet stars within a galaxy are even more distant from each other than planets within a solar system. If you scaled down the solar system so that Earth was the size of a marble, you'd need a stadium or two to hold all the planets. But if you scaled down the galaxy the same way, it would be thousands of miles across. The empty space would be unimaginable. Between galaxies, the distances become even larger. The Andromeda Galaxy is 2.5 million light-years away. That's about 25 times farther than the nearest star. And Andromeda is a neighbor. There are galaxies billions of light-years away. The universe is mostly empty space. The matter in it, stars, planets, gas clouds, is extraordinarily sparse. If you could somehow fill the entire galaxy with water, most of it would be empty. Space is the dominant feature of the cosmos. Distance is the defining characteristic. Everything is so far from everything else. How vast the universe truly is. We have numbers. 2 trillion galaxies. Hundreds of billions of stars per galaxy. But numbers don't convey the true vastness. The human brain cannot comprehend such scales. We evolved in a world of trees and animals and distances measured in miles. Our intuition fails at cosmic scales. Imagine you're driving a car at 60 miles per hour. To drive to the nearest star at that speed would take about 48 million years. The entire history of humanity is just a moment in that journey. A light year is about 5.88 trillion miles. The farthest objects we see are over 130 trillion miles away. No, that's not enough zeros. Over 1 billion trillion miles away. The numbers become absurd. They lose meaning. Our minds cannot build models of such scales. We can only accept them as facts and marvel. The universe is not just large. It's so large that the concept of largeness breaks down. It's not just empty. It's so empty that the concept of emptiness becomes inadequate. Within this vastness, life exists on at least one world. Conscious beings have emerged, and we gaze outward, trying to comprehend the scale of our home. The universe dwarfs us. It makes us insignificant, yet we persist in wondering about it. This courage, this determination to understand despite our smallness, may be the most remarkable feature of consciousness itself. The concept of infinite space. Is the universe infinite? Does space extend forever in all directions? Or is it finite, with some kind of boundary or curvature that brings you back to where you started? The question is profound. An infinite universe means there's always more, forever more. Somewhere infinitely far away, there's another galaxy. And beyond that, another. And beyond that, another forever. A finite universe means space ends somewhere. But if it ends, what's beyond the edge? These questions puzzle cosmologists. The mathematics of relativity allows for both possibilities. Space could be infinite and flat. It could be finite and curved, like the surface of a sphere. It could have other topologies we've barely imagined. Current observations suggest the universe is either infinite or so large that the difference is meaningless. We see no evidence of edges or boundaries. We see no evidence that space curves back on itself. The universe appears flat on the largest scales we've measured. If it's flat and infinite, then space truly goes on forever. There would be infinite matter, infinite stars, infinite worlds, and somewhere in that infinity, every possible arrangement of atoms would be realized. If this is true, then somewhere, conditions exactly like Earth exist. Somewhere, another version of you reads another version of these words. The implications are staggering, yet we cannot prove the universe is infinite. We can only study the part we observe and make educated guesses about the whole. Could the universe be finite after all? What if the universe is finite? What if space curves back on itself? Einstein's equations permit this. A finite universe would have no edge. You could travel in one direction forever, and eventually return to where you started. Like traveling around the surface of a sphere, you never hit an edge. Yet the surface is finite. Such a universe would contain only a finite amount of matter. All the stars and galaxies ever made would fit in a finite space. This is a profound difference from an infinite universe. A finite universe has a definite total size. It has a total amount of stuff. If we could measure these, we'd know something fundamental about reality. But how can we tell if the universe is finite? One way is to look for patterns in the cosmic microwave background. If the universe is finite and small enough, light could have traveled around it multiple times. This would create repeating patterns in the background radiation. We've looked for these patterns. We haven't found clear evidence of them. So either the universe is infinite, or it's finite, but too large for its curvature to be apparent in our measurements. We may never know for certain. The edge of the observable universe is our limit. Beyond that, the universe's true nature remains a mystery. What we can say is that the universe, whether finite or infinite, is truly vast, larger than human imagination. The shape of everything. The shape of the universe matters, not just for abstract mathematics, but for its destiny. If the universe is flat, it will expand forever, becoming ever colder and emptier. If it's positively curved like a sphere, it might eventually recollapse. If it's negatively curved like a saddle, the expansion would accelerate even faster than we observe. Current measurements suggest the universe is remarkably flat, so flat that we're puzzled. The geometry should have changed over billions of years due to matter, yet it remains flat. This puzzle led to the discovery of inflation, the idea that the universe expanded exponentially in the first fractions of a second after the Big Bang. Inflation would flatten the universe, explaining its current flatness. The shape of space on small scales is also interesting. Near black holes, space becomes warped. Around massive galaxies, space is curved. On average, over the largest distances, the universe appears homogeneous and flat. But if you zoom in on smaller regions, the shape becomes complex. Space is curved by matter and energy. It's a dynamic, ever-changing geometry. The universe's shape is not an idle question. It connects to fundamental physics. It connects to quantum mechanics. It connects to the ultimate fate of everything. Understanding the shape of the universe means understanding reality itself. The flow of time through the cosmos. Time flows, but does it flow uniformly throughout the cosmos? Einstein taught us that time flows at different rates depending on gravity and motion. Near Earth, time flows at one rate. Near the Sun, it flows slightly faster. Near a black hole, it flows dramatically slower. So what is the time of the universe? Is there a universal clock? In a sense, yes. Physicists define a cosmic time coordinate that measures the age of the universe. It's like a master clock that ticks at the rate of the cosmic expansion. But this is a theoretical construct. In reality, each observer has their own time, their own clock, and all these personal times are equally valid. This is the relativity of simultaneity. Events that are simultaneous for one observer are not simultaneous for another. This does not lead to chaos, because physics is consistent. The laws are the same for all observers. Events can be ordered causally, even if different observers disagree about whether they're simultaneous. Time flows, but it flows differently everywhere. It slows near gravity. It varies with motion. Yet somehow, the universe remains coherent. Causality is preserved. The arrow of time points forward everywhere. These things are subtle, paradoxical even, yet mathematics describes them perfectly. Time is perhaps the most mysterious aspect of the cosmos. We experience it as a flow, a river carrying us forward, but relativistic physics suggests something far stranger. How time began with the Big Bang. Time was not always here, at least not in the form we understand it. Before the Big Bang, time did not exist. There was no before. This is not poetic language. It's what the mathematics of general relativity suggests. Time is connected to space. They're woven together. When space came into being at the Big Bang, time came into being with it. In the first infinitesimal moment after the Big Bang, the universe was incredibly hot and dense. The laws of physics, as we know them, break down. We cannot say what happened then. Our theories fail, but we know that time itself was born. And from that moment on, time has been flowing. The universe has been aging. Stars have formed and died. Planets have emerged. Life has appeared. And now, billions of years later, conscious beings gaze backward through time, using the light of distant objects to reconstruct history. Time began with the Big Bang. It will end when the universe reaches its final state, unless the universe is eternal and cyclical, repeating forever, or unless there are aspects of time we don't yet understand. The beginning of time is one of the deepest mysteries. It connects cosmology to quantum mechanics. It bridges the largest scales to the smallest, and it remains partially unknown. What came before the beginning? This is perhaps the most unanswerable question. What came before the Big Bang? The truth is, this question may be meaningless. If time began at the Big Bang, then there was no before. The word before implies an earlier time, but if time itself began, there can be no earlier time. So asking what came before is like asking what's north of the North Pole. It's a question that dissolves when examined carefully. Yet physicists have speculated. Perhaps our universe is one of many. Perhaps there are infinite universes, each with its own Big Bang. Perhaps our universe is cyclic, expanding and contracting eternally. Perhaps what we call the Big Bang is actually a transition from one state to another. These ideas remain speculative. We have no evidence. Our theories don't extend back to the moment of the Big Bang. They break down at singularities, points of infinite density. Future theories might resolve these paradoxes, or we might find that some questions about the origin are forever beyond our ability to answer. The humility to accept that we don't know everything is part of being a good scientist. We can follow our understanding to the edge of the beginning, but beyond that edge, mystery remains. The arrow of time. Time has direction. It points forward. We remember the past. We can influence the future, but we cannot remember the future or influence the past. This asymmetry is profound. It's called the arrow of time. Why does time have direction? The answer relates to entropy, the measure of disorder in a system. Entropy always increases. A cup of coffee cools down. Ice melts. Order becomes disorder, never the reverse. If you watch a movie of these processes backward, it looks wrong. Ice forming spontaneously from warm water, coffee becoming hot in a cold room. These violate our intuitive sense of time's direction. The arrow of time emerges from entropy. Processes that increase entropy are allowed. Processes that decrease entropy are not, for all practical purposes. The universe began in a state of very low entropy. Everything was uniform and hot. As time passed, the universe cooled. Matter clumped into structures. Stars and galaxies formed. The universe became more ordered, yet overall entropy increased. How can order emerge while entropy increases? The answer is that local regions can become more ordered if the overall entropy of the universe increases. Our local region, Earth, has become more ordered because energy is being radiated into space. The universe, as a whole, becomes more disordered. Time's arrow is not a mystery in the way the Big Bang is. We understand it in terms of entropy, but the question of why the universe began in such a low entropy state remains open. Why time only moves forward? We live in the forward direction of time. We cannot go backward. This is not because of some law preventing time travel. It's because the underlying physics is asymmetric. The laws of physics themselves are asymmetric. Under time reversal, entropy always increases. This asymmetry creates the arrow. But here's a puzzle. The fundamental laws of physics, quantum mechanics and relativity, are symmetric under time reversal. If you reverse the direction of time in the equations still work. Yet in the macroscopic world, time has a clear direction. How can the symmetric microscopic laws produce an asymmetric macroscopic world? The answer involves probability and statistics. On the microscopic level, processes can go either direction, but some directions are more probable than others. An unstable particle can decay forward in time. The decay products could theoretically reassemble backward in time, but the probability of reassembly is infinitesimally small. It's so improbable that it never happens in practice. The arrow of time emerges from this probabilistic asymmetry. The laws are symmetric, but they allow for asymmetric behavior. The universe began in an improbable state of low entropy. From there, it evolved toward high entropy. This drives time forward. We are swept along in that current. The mystery of entropy. Entropy is disorder. But more precisely, entropy is the number of ways a system can be arranged at a given energy level. The glass of hot water is ordered. All the molecules are roughly in the same state. As it cools, the molecules can be arranged in vastly more ways. The number of possible arrangements increases, so entropy increases. The second law of thermodynamics states that entropy always increases in a closed system. This seems obvious at first. Of course, a hot cup cools down. Of course, ice melts in warm water. But think deeper. Why doesn't heat flow backward from a cold object to a hot object? Certainly the laws of motion would allow it. Individual molecules can transfer energy in any direction. Yet collectively, heat flows from hot to cold. This happens because there are vastly more arrangements of molecules consistent with heat flowing from hot to cold than consistent with heat flowing from cold to hot. The mathematics makes cold to hot flow so improbable that it's effectively impossible. Entropy is ultimately about probability. The universe evolves towards states that are more probable. Low entropy states are improbable. High entropy states are probable. The universe began in an incredibly improbable state of low entropy. It has been evolving toward higher entropy ever since. This is why time has a direction. This is why the past is different from the future. How order turns to chaos. Left alone, ordered systems become chaotic. A neat room becomes messy. A deck of cards, shuffled, returns to disorder. A hot object cools to room temperature. These processes are irreversible. You never see the reverse. This happens because disorder is more probable than order. There are vastly more ways for things to be disorganized than organized. Given time, any system will naturally evolve toward disorder. Yet life is ordered. Organisms are complex, structured, highly organized. How can life maintain order in a universe that tends toward chaos? The answer is that life does not violate the second law. Rather, life increases the total entropy of the universe. An organism maintains its order by consuming energy and excreting waste. The organism becomes more ordered, but the universe becomes more disordered. The total entropy increases. Life creates islands of order in a sea of increasing chaos. But these islands can only persist as long as energy flows through them. When that energy source ends, when the sun dies, these islands of order will fade. All the structure will dissolve into chaos. Eventually, the universe will reach a state of maximum entropy called heat death. No more structure, no more order, just uniform, cold, dead space. But that is billions and billions of years away. For now, order persists and life flourishes. Time and the life of the universe. The universe has a history. It was born, it's growing old, and someday it will die. The timeline is almost incomprehensibly vast. The Big Bang occurred about 13.8 billion years ago. The sun formed about 4.6 billion years ago. Life on Earth emerged about 4 billion years ago. Humans appeared only about 300,000 years ago, and civilization only about 10,000 years ago. From the perspective of cosmic time, humans are brand new. We're infants in a universe that's already ancient, yet the future extends even farther. The sun has about 5 billion years left before it exhausts its fuel and dies. After that, the planets will drift in darkness. Stars will continue to form and die for trillions of years. Eventually, even the most long-lived stars will burn out. The universe will become cold and dark. This is heat death. It's the far future of the cosmos. Time will continue to pass, but nothing will change. No more stars, no more planets, no more life, just eternal silence and cold. This is the arrow of time, taken to its logical conclusion. The universe begins in a hot, dense, ordered state. It ages, structures form and decay. Entropy increases. Eventually, it reaches a state of maximum disorder and stays there forever. Time continues, but time means nothing when nothing changes. This is the ultimate fate if the universe continues as it has. The stretching of space as time moves on. As time passes, space expands. The cosmic expansion is ongoing. Every moment, new space is being created. Galaxies are moved farther apart. This expansion is not uniform in time. It has been slowing down due to gravity. But then, a few billion years ago, it began accelerating. Dark energy now dominates. The expansion is speeding up. In the far future, expansion will continue to accelerate. Galaxies will move apart faster and faster. Eventually, galaxies will be so far apart that the light from one galaxy cannot reach another before the expansion carries them beyond each other's cosmic horizon. The universe will appear empty to any observer. They'll see only their own galaxy. All the others will be hidden by expansion. Time and space are connected. The expansion of space is driven by time passing, or, seen differently, time passes differently, depending on how space is expanding. In a flat, empty universe, time passes at a uniform rate. In our universe, with matter and dark energy, time passes at a slightly different rate in different places. But the overall effect is that the universe expands and time flows forward. Space stretches, time moves on, and the universe ages. The birth of stars and the passage of ages. In the beginning, there were no stars. The universe was pure energy and simple particles. Then gravity began to work. Matter clumped, hydrogen clouds formed, and eventually, after millions of years, the first stars ignited. These stars lived short, brilliant lives. They fused hydrogen into heavier elements. When they died, they scattered these elements into space. The next generation of stars formed from this enriched material. Each generation left behind heavier elements: silicon, iron, oxygen, carbon, nitrogen, the building blocks of worlds and life. Stars mark time in the universe. They live for millions or billions of years. Their lifetimes are our calendar. We speak of cosmic ages, the age of the universe, the age of the sun, the age of Earth. These are measured in the lives of stars. If we could see time accelerated, stars would be like mayflies. They'd flash into existence, burn brilliantly, and fade. Yet each star is billions of years old. Each one is ancient beyond human comprehension. Looking at the stars is looking at time itself. The nearest stars are only a few billion years old, but the most distant stars we see are billions of years old and are now dead or dying. Their light carries messages from the past. In that light is written the history of time. The birth of stars marks the beginning of structure. Without stars, there would be no galaxies, no life, no observers. Stars are how the universe becomes complex, the life and death of galaxies. Galaxies are born when vast clouds of gas collapse under gravity. The collapse heats the gas, igniting nuclear fusion. Stars form by the millions and billions. A young galaxy is brilliant. It's full of young, hot blue stars. It's actively forming new stars. As time passes, galaxies change. They consume gas and form stars at a slower rate. Their stars grow old and die. The galaxy becomes redder, filled with older stars. Mergers between galaxies are common. They can trigger bursts of star formation. They can create active galactic nuclei, powered by supermassive black holes. Over billions of years, galaxies evolve. They become less active. They form fewer new stars. Eventually, they become quiescent. Most of their stars have died. No new stars are born. The galaxy becomes a dead remnant, full of ancient stars and black holes. This is the fate of galaxies in an accelerating universe. Eventually, expansion will carry them so far apart that they cannot merge anymore. Each galaxy will be alone, and over trillions of years, the remaining stars will slowly die. Galaxies will fade into darkness. Nothing remains, just empty space and time flowing on. The life of a galaxy spans billions of years, but even that is temporary. On cosmic scales, time erodes all things. Even galaxies eventually fade away. Black holes and the end of time. At the heart of most galaxies, there's a supermassive black hole. These objects are places where space is curved so severely that nothing escapes, not even light. Near a black hole, time behaves strangely. It slows down. At the event horizon, the point of no return, time essentially stops relative to distant observers. Yet for something falling into a black hole, time passes normally. They don't notice anything special. As they cross the horizon, they only notice when tidal forces begin to stretch them apart. Black holes are laboratories for testing extreme relativity. They're places where space-time is warped beyond imagination, and they're places where time itself seems to end. A black hole is also a portal to understanding entropy and thermodynamics. Black holes have entropy. They emit radiation and slowly evaporate. In a sense, black holes are the ultimate fate of all matter. Given enough time, even black holes decay. They evaporate completely. Everything falls into black holes, and black holes eventually fade away. This is the ultimate end of matter in the universe. It takes an incomprehensibly long time, but it happens. Time continues, but all structure is gone. What happens at the edge of a black hole? The edge of a black hole is called the event horizon. It's the point of no return. Cross it, and you cannot escape. But here's something strange. At the horizon, nothing dramatic appears to happen. No barrier, no wall. Space is curved, but smooth. An observer falling through the horizon wouldn't notice anything special at the moment of crossing. They'd only notice when tidal forces, the stretching effect of gravity, became strong enough to harm them. But farther down, where space-time is more curved, tidal forces increase dramatically. If the black hole is small, tidal forces at the horizon are strong. But if the black hole is supermassive, an observer could cross the horizon without noticing. They'd have time to observe the universe beyond the horizon. They'd see strange things. Time would appear strange to them. From their perspective, outside observers move in fast motion. They'd see the entire future of the universe. Then, as they fell deeper, they'd approach the singularity, the center where space-time curvature becomes infinite. This is where our understanding breaks down. Physics fails. What actually happens at the singularity? We don't know. A black hole is a place where time reaches its extreme. It's a place where our theories need new insights. The point where time stops. At the event horizon of a black hole, time stops, or nearly stops, depending on perspective. From the viewpoint of a distant observer, a clock falling into a black hole appears to slow down as it approaches the horizon. Its clock ticks slower and slower. The light from the clock becomes redder and fainter. Eventually, the clock appears to stop entirely. It seems frozen at the horizon, ticking infinitely slowly. But from the clock's perspective, it falls right through. It experiences normal time passing. This is the relativity of time. The same event looks different to different observers. A black hole reveals something profound. Time is tied to position and motion. Time doesn't just pass. It flows at rates that depend on gravity and velocity. Near strong gravity, time slows. This is not an effect of clocks being broken. It's a genuine property of time itself. At the extreme of a black hole, time behaves in ways our intuition cannot grasp. The event horizon is not a place. It's a boundary in space-time. It's where the future light cones of events point inward into the black hole. Beyond the horizon, there is no future outside. All futures lead inward. For something at the horizon, time has no outward direction, only inward. This is the end of time in a local sense, not the end of time itself, but the end of outward-pointing futures. Wormholes and shortcuts through space. Einstein's equations allow for something called wormholes, tunnels through space-time connecting distant regions. If they exist, a wormhole could be a shortcut through space. Travel through the wormhole, and you'd arrive at a distant location faster than light could travel through normal space. You might even arrive before you left. From the perspective of certain observers, wormholes are mathematically possible, but do they actually exist? Probably not. Creating and maintaining a wormhole would require exotic matter with negative energy density. We've never observed such matter. It might not exist. And even if it did, keeping a wormhole open would be monumentally difficult. The wormhole would collapse unless held open by this exotic material. Still, wormholes capture the imagination. They represent the possibility that space might have shortcuts, that reality might not be as simple as we think. The universe might have topology we haven't imagined. Wormholes also connect to time travel, another possibility lurking in Einstein's equations. Some solutions of general relativity permit closed time-like curves, paths through space-time that loop back on themselves. If you traveled such a path, you could arrive at your own past. This seems to violate causality. How can you change your past? These paradoxes suggest that either wormholes don't exist, or nature prevents their use for time travel. The universe might have built-in protections against paradox. For now, wormholes remain theoretical, but they remind us that space-time might be stranger than we imagine. Could we ever travel through time? Time travel backward seems impossible. It violates our sense of causality. Yet Einstein's equations permit it. In principle, certain geometries of space-time allow for closed time-like curves. A rotating black hole might create such curves. A wormhole might connect different times. Some cosmological solutions involve time loops. If these things exist, they might allow time travel. But there are problems. First, creating and maintaining the necessary space-time geometries would require technology far beyond our reach. Second, nature might forbid time travel through unknown mechanisms. Some physicists believe the laws of physics include hidden protections against paradox, a principle of self-consistency, they call it. Under this principle, time travel might be possible, but only in ways that don't create paradoxes. You cannot change the past, but you can be part of it. Your attempt to change the past was always part of history. The timeline is self-consistent. Is time travel possible? Probably not in any practical sense, but it's not forbidden by the known laws. The question remains open, and the possibility, however remote, reminds us that time might be far stranger than we experience. The paradox of time travel. Imagine you travel back in time and kill your grandfather before your parent was born. Then you were never born, so you never traveled back in time, so your grandfather survived. So you were born, so you did travel back in time. This is the grandfather paradox. It seems to lead to logical contradiction, self-reference loops, impossible situations. If time travel is possible, how can such paradoxes be avoided? Several solutions have been proposed. The many worlds interpretation suggests that traveling back in time creates a branch in the timeline. You kill your grandfather in a parallel universe, but not in your original one. You were still born. The timeline splits. Another solution is the self-consistency principle. The universe constrains events so that paradoxes never arise. You cannot kill your grandfather because something always prevents it. A gun jams. You miss. You change your mind. The universe ensures consistency. A third solution is that time travel to the past is fundamentally impossible. The laws of physics, properly understood, forbid it. We don't yet know which is correct, but the grandfather paradox shows that time travel, if possible, raises profound questions about causality and reality. It suggests that the relationship between cause and effect might be more complex than we imagine. The twin paradox explained. Two twins are born, one stays on Earth. The other travels to space, at near light speed, circles a distant star, and returns. When they meet again, the traveling twin has aged less than the earthbound twin. They were born at the same time, but now they're different ages. This is the twin paradox. It seems paradoxical because special relativity says that motion is relative. Shouldn't both twins experience the other as moving? Shouldn't both age more slowly? The resolution is that acceleration breaks the symmetry. The traveling twin accelerates away from Earth, orbits the star, and accelerates back. The earthbound twin never accelerates. Because of this asymmetry, their experiences are not equivalent. The traveling twin really does age less. This is not illusion. It's not a matter of perspective. The traveling twin is genuinely younger when they reunite. This has been verified experimentally. Atomic clocks, flown on airplanes, age slightly less than identical clocks on the ground. The effect is tiny but real. The twin paradox demonstrates that time is not absolute. Duration depends on motion. It shows the power of relativity to make predictions that seem impossible yet are true. The paradox also shows the limits of relativity. It takes two observers with different histories to resolve it. Symmetry in motion doesn't lead to equivalent aging. How time slows near strong gravity. Gravity slows time. The stronger the gravity, the more time slows. This is not metaphor. Clocks in strong gravity tick more slowly than clocks in weak gravity. An observer on the surface of Earth ages slightly slower than an observer far from Earth in free space. The difference is tiny. A year on Earth's surface lasts about 1 nanosecond, less than a year in space, but it's real. GPS satellites must account for this. Their clocks experience weaker gravity at altitude, so they tick faster than Earth's clocks. If we didn't adjust for this, GPS would accumulate errors. Near a black hole, the effect becomes extreme. At the event horizon, time runs infinitely slowly compared to distant observers. An observer watching someone fall into a black hole sees them slow down as they approach the horizon. The infalling person appears to freeze. Their clock appears to stop. Yet from the infalling person's perspective, they cross the horizon in finite time. Time continues to pass for them. They don't notice anything special, but their clock really does run slower than distant clocks. Gravity and time are intertwined. Strong gravity means slow time. This is one of the greatest insights of general relativity. It shows that gravity is not a force in space and time, Rather, gravity is the curvature of space-time itself. The clocks of the universe. Throughout the universe, clocks tick at different rates. A clock near the sun ticks slower than a clock far from the sun. A clock on Earth's surface ticks slower than a clock in space. A clock in a moving spacecraft ticks slower than a clock at rest. Every object has its own proper time, the time measured by a clock moving with it, and this proper time runs at different rates, depending on velocity and gravity. Yet physics remains consistent. All observers can agree on what happens, even though they disagree on duration. The laws of physics are the same for all. This is the genius of relativity. It accommodates the relativity of time while preserving the consistency of physics. Physicists define a cosmic time, a time coordinate that measures the age of the universe on average. But this is a theoretical construct. In reality, every observer has their own time, and all these personal times are equally valid. The universe contains multitudes of clocks, each ticking at its own rate. Each clock keeps proper time, yet somehow, causality is preserved. Events follow a logical order. Causes precede effects. The universe is coherent, despite the relativity of time. This is remarkable. It's a testament to the deep structure of reality. Measuring time across the stars. How do we measure time on cosmic scales? We use pulsars, rapidly spinning neutron stars that emit regular pulses of radiation. Some pulsars are so stable that they rival atomic clocks. We use supernovae of a particular type as standard candles to measure distance and time. We observe galaxies at different distances and infer their ages. We measure the cosmic microwave background and extract information about the age of the universe. All these methods rely on light carrying information across space and time. Light tells us about the past. And by analyzing light from distant objects, we reconstruct the history of the universe. We measure stellar ages by analyzing their spectra. Young stars are blue and hot. Old stars are red and cool. We can identify stars at different evolutionary stages and build a timeline. We measure the age of the universe by observing the cosmic expansion rate and tracing it backward to the Big Bang. All measurements rely on understanding how light carries information, and all measurements must account for relativity, the fact that time runs at different rates in different places. Measuring time across the stars requires understanding both physics and light. It requires instruments of exquisite sensitivity, and it reveals that the universe has a history spanning billions of years. Atomic clocks and universal precision. The most precise clocks ever built are atomic clocks. They measure time by counting the vibrations of atoms. A cesium atom vibrates at a frequency so consistent that it defines the second itself. Modern atomic clocks are accurate to within 1 second in billions of years. They're so precise that we can measure relativistic effects directly. Atomic clocks flown on airplanes have been observed to age slower than identical clocks on the ground. The difference is tiny, but it's measurable. Atomic clocks in different gravitational fields tick at different rates. This is the foundation of GPS. Satellites in orbit have atomic clocks that run faster than Earth-based clocks due to weaker gravity and orbital motion. The satellites must constantly correct their clocks. Without this correction, GPS would accumulate errors of miles per day. Atomic clocks are tools for exploring relativistic physics. They're instruments for measuring the universe. They reveal that time is not what it seems. Time is not uniform. It's not absolute. It's woven into space-time and varies with position and motion. These tiny clocks measure the deepest truths about reality. There are windows into the structure of space-time itself, and they confirm over and over that Einstein was right. The relativity of now. What does now mean? It seems obvious. Now is the present moment, but relativity shows that now is relative. Events that are simultaneous for one observer are not simultaneous for another. This is the relativity of simultaneity. An observer on Earth and an observer on a spacecraft moving at high speed will disagree about which events happen at the same time. Neither is wrong. Both are correct from their own perspectives. This seems to violate common sense, but it flows naturally from the constancy of light's speed. If light always travels at the same speed for all observers, then the concepts of space and time must be relative. Different observers moving relative to each other must have different notions of what events are simultaneous. There is no absolute present moment. There is no universal now that all observers share. There are only local notions of present relative to each observer. This has profound implications. If there is no absolute present, then all moments might exist equally. The past, present, and future might all be equally real. We might live in what physicists call the block universe, where all moments exist together in a static space-time, or there might be a preferred reference frame in which one moment is truly the present. The nature of now remains one of the deepest mysteries in physics. Does the present truly exist? Is the present moment real? Or is it an illusion created by consciousness? Physicists debate this. Some argue that only the present exists. The past is gone. The future hasn't happened yet. The present is the only real moment. This view aligns with our intuition, but it conflicts with relativity. If there's no absolute present, which moment is real? Different observers disagree on which moment is the present. Others argue that all moments exist equally, past, present, and future. We experience time as flowing from past to future, but this is an illusion. All moments exist in the block universe, frozen in space-time. We move through this block from past to future, but the future already exists. This view is consistent with relativity, but it seems to rob time of its meaning. If the future already exists, how can we change it? If the past still exists, why can't we access it? These questions touch on the nature of consciousness and free will. Do we choose our future, or is the future already written? Physics doesn't answer these questions definitively, but relativity shows that time is not as simple as it seems. The present might not be what we think it is. The idea of the block universe. Imagine space-time as a four-dimensional block, 3 dimensions of space, 1 of time. All moments exist within this block simultaneously. Past, present, and future are all there, equally real, equally present. This is the block universe. In this view, time doesn't flow. Change is an illusion. Or rather, change exists within the block, but the block itself is static. We experience time as flowing because we move through the block from past to future. Our consciousness travels along a world line through space-time. From our perspective, the present moment advances, but from a timeless perspective, all moments are equally present. This view emerges naturally from relativity. Space and time are woven together. Space-time is a single entity. It has no temporal direction. It simply is. The block universe seems counterintuitive. It suggests that free will is an illusion. If the future already exists in the block, how can we choose it? Yet some physicists accept the block universe as the most consistent interpretation of relativity. Others reject it, arguing that the present moment is genuinely real and the future is genuinely open. The debate continues. The block universe represents a radically different way of thinking about time. It challenges our everyday experience, yet it flows from the mathematics of relativity. Are the past and future already written? If the block universe is true, then yes, the past and future already exist. They're already written in the fabric of space-time. Everything that will happen has always been happening, in a sense. The universe is a static, four-dimensional entity. We move through it. We experience it as flowing, but it's not changing. It simply is. This raises profound questions about free will. If the future is already determined, how can we make free choices? Physicists who accept the block universe often argue that free will and determinism are compatible. We make choices, Our choices determine our future, but the future determined by our choices already exists in the block. We're not free to choose a different future. We're only free to make the choices that we do make, which determines the future that was always going to happen. This is compatibilism. Free will and determinism coexist, but other physicists reject the block universe. They argue that the present moment is genuinely real and the future is genuinely open. The future is not written. It's made as time progresses. We truly have free will. Which view is correct? Physics doesn't settle this. The mathematics of relativity is compatible with both. The question of whether the future is open or closed remains a matter of interpretation and philosophy. The flow of time in quantum mechanics. Quantum mechanics adds another layer of mystery to time. In quantum mechanics, the future is not deterministic. A particle doesn't have a definite position or momentum until it's measured. Before measurement, it exists in a superposition of all possible states. Only when measured does it collapse into a definite state. This introduces genuine randomness into physics. And the future is not written. It's genuinely open. Yet quantum mechanics also has a flow of time. The wave function evolves according to the Schrödinger equation. Measurements occur. Outcomes are produced. There's a direction to time in quantum mechanics. But this direction emerges from the increase of entropy, not from the equations themselves. The equations are reversible. The arrow of time is not built in. How quantum mechanics and general relativity combine to describe time remains an open question. They're incompatible as currently formulated. A theory of quantum gravity would resolve this. It would show how time flows in a quantum universe. It would show whether the future is open or closed, whether free will is real or illusory. Until then, time remains mysterious, even at the quantum level. Can time exist without change? If nothing ever changes, if everything is static, does time still exist? This is a profound question. Our intuition says that time requires change. Without change, time has no meaning. But mathematics allows for static spacetime. The block universe is static. Nothing changes. Yet time exists as a dimension. Events are separated by temporal intervals. Is this time? Or is it something else? Some philosophers argue that time requires change. Without change, there's no time, only eternity. Others argue that time is simply another dimension, like space. Space doesn't require change. Neither does time. The block universe is a static object, but it contains temporal dimension, just as a map has spatial dimensions, but doesn't change. Space-time has temporal dimension, but doesn't change. Which view is correct? It depends on how you define time. If time is the measure of change, then without change, there's no time. If time is a dimension of space-time, then time exists even without change. The question reflects the deep mystery of time's nature. Is time something fundamental, or is it an emergent property of a universe undergoing change? Physics doesn't yet provide a definitive answer. The expanding space between moments. Time flows. Moments succeed each other. But what is the space between moments? What separates one instant from the next? In physics, this is represented by the interval, a combination of space and time distances. The interval is what remains constant for all observers. Different observers measure different spatial and temporal intervals, but the interval, the space-time distance, is the same. This interval is the true separation between events. Moments are not equally spaced. The separation between moments depends on the observer's motion and position in gravity. For a stationary observer on Earth's surface, moments pass at one rate. For a moving observer, moments pass at a different rate. The space between moments is not uniform. It expands near massive objects, where time runs slower. The space between moments contracts far from massive objects, where time runs faster. The universe contains multitudes of different temporal flows. Each observer has their own rhythm of time. The space between moments is different for each, yet all observers can agree on the underlying space-time geometry. All can agree on what happens. The expanding space between moments is a consequence of gravity and motion, so the reminder that time is woven into space-time, not separate from it. The future of time in an endless universe. If the universe is infinite and endless, what is the future of time? Time will continue forever, moment after moment, forever. The universe will expand. Stars will burn out. Galaxies will fade. Entropy will continue to increase. Eventually, the universe will reach a state of maximum entropy called heat death. All structure will be gone. The universe will be a uniform sea of particles in thermal equilibrium. Time will continue, but nothing will change. No clocks will exist to measure time. No consciousness will exist to experience it. Time will flow through an empty, dead cosmos, forever and ever. Or perhaps not forever. Perhaps time itself will end. Perhaps at some point, no more moments can occur. Time will reach an end state. This seems paradoxical. How can time end? If time ends, what comes after? These questions suggest that our understanding of time might be incomplete. Perhaps time, like space, is finite. Perhaps it has a beginning and an end. Or perhaps time is cyclic, repeating endlessly. Until we understand the ultimate fate of the universe, we cannot know the ultimate future of time. Will time ever come to an end? Can time end? Can there be a final moment beyond which nothing occurs? This seems contradictory. If there's a final moment, what comes after? The idea of time ending is difficult to conceive, yet physics allows for it in principle. In some cosmological models, the universe reaches a state beyond which nothing happens. The heat death scenario is one example. In another scenario, the universe could contract back to a singularity. Time would end when the universe ends. Both scenarios raise profound questions. If time ends, was it finite all along? Is time a creation of the universe, existing only while the universe exists? Does time end when all structure is gone? Or does time continue to flow even in a dead, empty universe? These questions touch on the nature of existence itself. They suggest that time might not be fundamental. Perhaps time is emergent, arising from the dynamics of the universe. When the universe reaches a static state, time might cease to exist, or time might continue to exist, but lose all meaning. For now, these remain speculations, but they remind us that time, despite its familiarity, remains deeply mysterious. The death of the cosmos. The universe will die. Stars will burn out. Galaxies will fade. Matter itself might decay. All structure will dissolve. This is the ultimate fate, unless something we don't understand happens. The death of the cosmos is not imminent. It will take trillions of years, but it will happen. The universe is aging. Time flows. Entropy increases. And eventually, the cosmos will reach an end state. What will that state look like? We don't know for certain, but current theories predict a universe of immense cold and darkness. All the stars burned out long ago. All the galaxies scattered beyond each other's horizons by expansion. Just empty space and a few lingering particles, slowly decaying. Perhaps some black holes remain, slowly evaporating through Hawking radiation, but eventually, they too fade away. The universe becomes a uniform sea of cold, dilute particles. No structure, no life.
No consciousness to observe it.
Time continues to pass, but time has no meaning. Nothing happens. The universe is dead. This is the heat death. It's a sobering vision of the far future. Yet from our perspective, it's so far away that it has little relevance. We live in the youth of the universe. Stars still burn. Galaxies still merge. Life still thrives. We have billions of years before we need to worry about the death of the cosmos, the heat death, and the final silence. Heat death is the fate of the universe. If current trends continue, the universe expands forever. Entropy increases forever. Eventually, all energy is evenly distributed throughout space. No structure remains, no gradients, no temperature differences. Everything is at the same temperature. Absolute zero. The universe reaches thermodynamic equilibrium. In this final state, nothing changes. No reactions occur. No processes happen. Time continues to pass. But time is meaningless. There is no change to measure, no clocks to keep time, no observers to experience time. Just eternal, silent, cold emptiness. Forever. Heat death is not a dramatic event. There's no explosion or collapse. Rather, it's a gradual fade. Stars burn out one by one. Black holes evaporate. Matter decays. Slowly, over inconceivably long timescales, all structure dissolves, and the universe reaches its final state. Some physicists find this vision depressing. All life, all civilization, all consciousness, ultimately meaningless. Everything ends in silence and void, but others find it liberating. It suggests that we live in a golden age. We exist when the universe is still young, still active, still full of possibility. That's remarkable. We should cherish it. Could time reverse itself? Can time go backward? Can the arrow of time reverse? This seems to violate fundamental principles. Entropy increases. Causes precede effects. Disorder grows. These things are asymmetric. They point time forward. Yet the fundamental laws of physics are symmetric under time reversal. If you reverse time in the equations, they still work. So why does time only go forward? The answer is entropy and probability. Low entropy states are improbable. High entropy states are probable. The universe began in an improbable state of low entropy. It has been evolving toward high entropy ever since. This creates the arrow. But what if the universe began to contract instead of expand? What if gravity could overcome expansion and pull everything back together? In a contracting universe, might entropy decrease? Might time reverse? Some physicists speculate about this. A cyclic universe that expands and contracts eternally. Each cycle might have time flowing forward in its forward phase and backward in its contracting phase. Or time might reverse when entropy reaches its maximum and begins to decrease. These ideas remain speculative, but they raise fascinating questions. Could we observe time reversed? Would we even recognize it? These are mysteries for future physics. What lies beyond time and space? Is there anything beyond time and space? Can we even ask this question meaningfully? Time and space, as we know them, are properties of the universe. The universe might be all there is. There might be nothing beyond it. Yet physicists speculate. Perhaps time and space emerge from something more fundamental. Perhaps there's a deeper level of reality where time and space don't exist. In quantum gravity, time might be emergent. In the quantum foam at the smallest scales, time might be fluctuating and uncertain. Perhaps what we call time is an approximation that works on larger scales. At the quantum level, time is not fundamental. Beyond time and space, what would exist? Information? Consciousness? Mathematical structure? These are philosophical questions. Physics has little to say about them, yet they point to the limits of our understanding. We understand the universe in terms of time and space, but these concepts might be limited. They might be tools that work within the universe, but break down at the most fundamental level. What lies beyond might be unimaginable to minds evolved in a universe of space and time. Or perhaps there is nothing beyond. Time and space are all there is, fundamental and irreducible, the eternal mystery of existence. Why does anything exist? Why is there a universe rather than nothing? These are perhaps the deepest questions. They're beyond the reach of science. They're questions of philosophy and metaphysics. Physics can describe how the universe works. It can trace the universe back to the Big Bang, but it cannot explain why the Big Bang happened, why there was something to begin with. We can ask why time began, but we cannot ask what came before, because before implies time. We can ask why space exists, but we cannot ask what's beyond space. These questions dissolve under scrutiny. They lose meaning, yet they persist. We want to know. We want to understand the ultimate why, and the universe, in its vastness and mystery, resists easy answers. Perhaps existence is fundamental. Perhaps there's no reason. It simply is. The universe is a brute fact. Accept it. Or perhaps one day, physics will advance far enough to answer these questions. A new theory will emerge that explains why the universe exists, why time began, why the laws are as they are. Until then, mystery remains, and in that mystery lies the endless appeal of science. There is always more to discover, always more to wonder about, always more mystery to explore. The universe is eternal in this sense, forever strange, forever mysterious, forever beautiful.